local function in generalized ideal topological spaces. This presentation is almost entirely based on the paper by Maitra, by Rajesh Tiwari and Tivari that was published in 2015. Basically, this will be about ideal topological spaces that are now widely recognized and studied by many authors, both in the context of classical and non-classical, that is, say, intuitionistic, fuzzy, vague, nutrosophic or soft sets. This will be about classical sets and about, as you can see, generalized topologies, while basically in the sense of Chasar. However, there is some difference. Our authors assume that both empty set and the whole universe are open, so they belong to our generalized topology, but in fact Chasar requires only this condition here. So I would say that the paper of our authors is rather about super topologies in the sense of Mashur. Be as it may, we have closure under arbitrary unions, but not necessarily under any intersections. As always, we say that members of our generalized topology are G open sets and their complements are G closed sets. The notions of interior and closure are standard. I think that you are already familiar with these two constructions. And then we have the concept of ideal on X. Well, ideal is any family of subsets of some universe such that if some set belongs to ideal and some of its subsets belongs to something is contained, some set is contained in A, then this contained set, this B, belongs to ideal too. So it's just closure under supersets. Moreover, we have closure under finite unions, which is depicted here. One can prove, moreover, that the intersection of two ideals is an ideal too. And then we define, our authors define, local function of A with respect to ideal I and generalized topology. This is here. This whole concept can be considered as a generalization of the idea of closure, in the sense that ideal is just like generalized empty set. This local function is the collection of those elements of our universe that, such that for each of their open neighborhoods, A intersected with such neighborhood is beyond the ideal. If our ideal collapses to this most basic case that our ideal is just empty set, it consists of empty set only, then this is replaced with different than empty set. Yes, non-empty. This intersection would be non-empty, and this would be just like closure. And this will be mentioned later. Here you have some example of such space with some universe, some generalized topology, and some ideal. And one can check that the following identities holds, that for these subsets local function is empty, but for these two subsets, these three subsets, together with the whole universe, local function is just like singleton of C. This is a matter of some calculations. Then we have the following properties that are mentioned in other papers too. They are here, that for example, if we have a union of two local functions with respect to the same ideal, then it's contained in the local function of the union of these two sets. That local function of local function is contained in this initial local function. The last property is interesting, that if one ideal is contained in another, then local function of this second set is contained in the local function of the first set. And then we have an interesting thing. First, the author proved the following result, that the intersection of ideal and generalized topology consists of empty set only, if and only if local function of the whole universe is identical with the whole universe. You can analyze the proof, you can stop the video here and you can check all those this whole reasoning. Basically, it's reproduced after our authors, but with some changes. First of all, there is a mistake in their original paper, because here they have empty set, not the singleton of empty set. It's written here, as you can see. This is their original paper. Here is their theorem. Clearly this doesn't make sense, because the intersection of any ideal with generalized topology is non-empty always, because empty set is always common for ideal and generalized topology. So here we have exactly this case, when the empty set is the only common element of these two families. And then we have this theorem, that if we have two ideals on X, then the union of local functions with respect to the same set A but with different ideals, as it's written here, it's contained in the local function of intersection of these two ideals. Local function of A with respect to the intersection of these two ideals. And the authors claim that equality doesn't hold. So this is their counterexample. One can check. We have generalized topology here, we have some ideal here, we have some another ideal here, and some set A which consists of A and C. And the authors calculate that the union of local functions, one with respect to I and another with respect to ideal J, this union is ABC, and it's different than local function of the intersection of these ideals. This intersection is just empty set, and this is like the whole X. And this is very interesting, because we couldn't find any mistake in their reasoning, but there are some other authors who say that the theorem above is an equality. Okay, let us analyze their arguments. If you don't believe, check this. This is one of these two papers, and here they suggest that it is equality. The same here. Okay, let us analyze their arguments. First, there is a paper by Al-Sharari. It's here, the one that is presented here. This star here is a typo, perhaps. His reasoning is: assume that X belongs to the local function of intersection of ideals, but it does not belong to the union of local functions. So it does not belong to this local function, and it does not belong to this local function. So we have some neighborhood of X such that the following identity holds, that U1 and A belongs to the ideal, and another neighborhood U2 such that the following holds, that U2 intersected with A is in ideal J. And then the author claims that the following holds, that the intersection of U1 and U2 intersected with A belongs to the intersection of these two ideals. So due to this fact, X does not belong to the local function of I and J. Does not belong to the local function because there is some neighborhood, alleged neighborhood here, such that its intersection with A falls into the ideal, into the intersection of ideals, which is an ideal too. But there is some problem. Well, we need G open neighborhood, but our topology is a generalized one, so we do not have closure under intersections, so we do not have any guarantee. I would say, maybe this is my mistake, but you can check this, we do not have any guarantee that this intersection of two G open sets is open too. So the problem is with this. Now let us analyze the reasoning of Tiwari and Rajesh. Let X belong to the local function of I and J intersected. Then for every G open set U containing X, we have the following, clearly. So this does not belong to ideal, or this does not be, or the same thing does not belong to this ideal. A and U does not belong to I, or A and U does not belong to J. And the authors claim, due to this reason, that it means that X belongs to local function of A with respect to I, or to the local function of A with respect to J. But take, for example, this case here. It requires a guarantee that for any G open neighborhood U of X, the following holds: that A and U does not belong to I. But from our earlier considerations, the only thing that we know for sure is that for any G open neighborhood U of X, this holds. Maybe the left side or maybe the right side. You know, the problem is that this P or Q then P is not a classical tautology, or in terms of first order logic, the fact that we have for all X, P of X or Q of X for some formulas P and Q, this doesn't imply that for any X P of X or for any X Q of X. And here you can analyze this taking the counterexample of Maitra and other authors. Take D in their counterexample, and here are just calculated. You can check these calculations that D does not belong to A star I nor to A star J, even if it belongs here. Okay. This is here, one of the neighborhoods of D does not belong to J, but it belongs to I, so we cannot say that D is in the local function of A with respect to I. And analogously here, yes, some neighborhood does not belong to I, but it is in J, so following holds. Okay, but you can check this. You should check it. I encourage you to analyze this reasoning. Then there are other theorems of our authors that, for example, local function is always contained in the original closure of A. So if A is closed in terms of G, then local function is contained in A. If our ideal consists of empty set only, then the local function is identical with the closure of A. It should be closure of A here. And in this extreme case, if our ideal is reduced to the singleton of empty set and A is G closed, then local function is identical with A, of course. But basically, this is the most specific case. We are interested in more complicated ideals rather, because we want to generalize the idea of empty sets, so we can define this kind of closure, the union of A and its local function, and prove that it's always contained in the original closure. And here finally you have the bibliography of this video, so you can check all these papers and analyze these reasonings. I encourage you to do this, and as always, thank you very much for your attention.